The sixth law of exponents is also known as the zero exponent rule. Now we're going to discuss case 2 of the quotient of powers rule, that is if m equals n. Since m equals n, we're going to substitute the numerator exponent m by n. So the expression is now a to the n over a to the n equals a to the power n minus n, where a is not equal to 0. That means a can be any real number except 0. Now n minus n equals 0, so this becomes now a to the power 0, or simply a to the 0 power. So a to the n over a to the n equals a to the 0 power. But a to the n over a to the n is equal to 1, because any number divided by itself except 0 equals 1. So by the transitive property of equality, if a is equal to b and b is equal to c, then a is equal to c. So if this quotient is equal to a to the 0 power, and the same quotient is equal to 1, therefore a to the 0 is equal to 1. Right there. So a to the 0 power equals 1. So we refer to this as the zero exponent rule. That means any non-zero base raised to the 0 power equals 1. So what's the significance of this? Back in the day, a couple of centuries ago, mathematicians were already familiar with the 5 basic laws of exponents, but only for positive exponents. They knew that positive exponents represent repeated multiplication of the base. Like, for example, the power a cubed. They knew that a cubed represents a base a multiplied by itself 3 times. So that's equal to a times a times a. Then they divided the power a cubed by its base a using the quotient of powers rule. So that's a cubed over a equals a to the power 3 minus 1. And that's equal to a squared. So dividing a cubed by its base a results in a squared. Then dividing further, a squared divided by its base a results in a to the first power. Then dividing a to the first power by its base a results in a to the 0 power. And that's when they stopped. They absolutely didn't have any idea about the 0 exponent. They thought that a to the 0 power was meaningless, even useless. What's a base multiplied by itself 0 times? What's a number raised to nothing? So they got stuck here for a very long time, until a new generation of mathematicians revisited this problem and recognized the consistency of the pattern, that each time a power is divided by its base, the exponent consistently decreases by 1. From a cubed, it became a squared, then a to the first, then a to the 0 power. So they zeroed in on this problem, a to the first divided by a. Now, using the quotient of powers rule, this is now equal to a to the power 1 minus 1. A being equal to a to the first. So this now becomes a to the 1 minus 1 is 0. So that's a to the 0 power. Then they focused on this, a to the first over a. They knew from an ancient arithmetic rule that a quantity divided by the same quantity equals 1. So a to the first over a equals 1. Likewise, they knew from an ancient logical reasoning that things which are equal to the same thing are equal to one another. So if this thing is equal to a to the 0 and the same thing equals 1, therefore a to the 0 is equal to 1. But the concept of 0 exponent was entirely new to them. So they pondered on this. They reflected deeply on this new idea, believing that there must be something significant about this. So they figured out that for this to be valid and true, it had to be consistent with the 5 existing laws of exponents. So to verify whether this would hold true, when the exponent became 0, they set n equals 0. So they tested a to the 0 equals 1 against all 5 laws of exponents. So they tested it first with the first law, which is the product of powers rule. That's a to the m times a to the n equals a to the power m plus n. So this becomes a to the m times a to the 0 power, because they set n equals 0. And that's equal to a to the m plus 0. But a to the 0 equals 1. So that's now equal to a to the m equals m plus 0 is m. So it's simply equal to a to the m. So a to the m equals a to the m. Both sides being equal, there's no contradiction. Therefore, a to the m equals a to the m is a statement of validation. So they concluded that a to the 0 equals 1 was consistent with the first law. Then they tested it against the second law, which is the power of a power rule. That's a to the m quantity raised to the n power equals a to the power m times n. So this becomes now a to the m raised to the power 0. Because they set n equals 0. That's equal to a to the m times 0. But the power a to the m raised to the 0 power is equal to 1. So this is now equal to 1. M times 0 is 0. So this becomes now a to the 0 power. but a to the 0 power equals 1. So that's now equal to 1 equals 1. So 1 equals 1. Both sides being equal, there's no contradiction. Therefore, 1 equals 1 is a statement of validation. Therefore, they concluded that a to the 0 equals 1 was consistent with the second law. Then they tested it against the third law, which is the power of a product rule. So the product ABC quantity raised to the n power equals a to the n times b to the n times c to the n power. So this becomes now the product ABC raised to the 0 power, because they set n equals 0. And that's now equal to a to the 0 times b to the 0 power times c to the 0 power. But the product ABC is raised to the 0 power. And that's equal to 1. That's a raised to the 0 power is 1 times b to the 0 power equals 1 times c raised to the 0 power equals 1. So that's 1 times 1 times 1 is 1. So 1 equals 1. So both sides being equal, there's no contradiction. Therefore, 1 equals 1 is a statement of validation. So they concluded that a to the 0 equals 1 was consistent with the third law. Then they tested it against the fourth law, which is the power of a fraction rule. So that's the fraction a over b quantity raised to the n power equals a to the n over b to the n. So this becomes now a over b raised to the 0 power, because they set n equals 0. And that's equal to a to the 0 power over b to the 0 power. But a over b, the 0 power, so that's equal to 1. A to the 0 power is 1. B to the 0 power is 1. So this becomes now 1 equals 1 over 1. Or simply 1 equals 1. So 1 equals 1, both sides being equal, there's no contradiction. Therefore, 1 equals 1 is a statement of validation. So they concluded that a to the 0 equals 1 was consistent with the fourth law. Then they tried it against the fifth law, which is the quotient of powers rule. That's a to the m over a to the n equals a to the power m minus n. So this becomes now a to the m over a to the 0 power, because they set n equals 0. And that's equal to a to the power m minus 0. But a to the 0 equals 1. So this is now a to the m over 1 equals a to the m. M minus 0 is m. So this is simply equal to a to the m. So a to the m equals a to the m. Both sides being equal, there's no contradiction. Therefore, a to the m equals a to the m is a statement of validation. So they concluded that a to the 0 equals 1 was consistent with the fifth law. So mathematicians have proven that a to the 0 equals 1 was consistent with all 5 existing laws of exponents. They realized that a to the 0 equals 1 was more than just a new idea. It was a logical necessity that a to the 0 must equal 1, because it is the only value that makes all laws of exponents consistent and free from contradiction. Then later on, they ventured into an uncharted territory. Continuing with the pattern, they divided a to the 0 by its base a. So, dividing a to the 0 power by its base a, that's a to the 0 divided by a. Now, using the quotient of powers rule, this becomes now a to the 0 minus 1. So this is now a to the power 0 minus 1 is minus 1. But a to the 0 equals 1. Having verified this to be valid and true, so this becomes now 1 over a. Or simply a to the minus 1 equals 1 over a. So this revealed a new idea that a base raised to a negative exponent is equal to the reciprocal of the base raised to its corresponding positive exponent. So this marked the birth of the negative exponent. So a to the 0 divided by a results in a to the minus 1. Or simply 1 over a. Dividing a to the minus 1 by its base a, that's a to the minus 1 over a. Using the quotient of powers rule, this becomes a to the minus 1 minus 1 equals a to the minus 2. So this is a to the minus 2, or simply 1 over a squared. So it's simply the reciprocal of the base raised to its corresponding positive exponent. So dividing a to the minus 2 by a, that's a to the minus 2 over a equals a to the power minus 2 minus 1 equals a to the minus 3. So this is now a to the minus 3, or simply 1 over a cube. So this showed that negative exponents simply represent repeated division by the base, just as positive exponents represent repeated multiplication of the base. So a to the 0 equals 1 became the bridge point that connects positive and negative exponents. So because of this, they were able to mix positive 0 and negative exponents in a single expression. Like, for example, a squared times b to the 0 times c to the minus 4. That's equal to a squared times b to the 0 is 1 times 1 over c to the 4th power. This being equal to the reciprocal of the base c raised to its corresponding positive exponent. And that's equal to a squared times 1 times 1 is a squared over c to the 4th power. Now, as per the zero exponent, let's say 9 raised to the 0 power. The base 9 is non-zero, and it is raised to the 0 power, therefore that is simply equal to 1. How about minus 9 raised to the 0 power? So the zero exponent applies only to the base 9, and that is independent of the negative sign before it. So 9 being a non-zero base raised to the 0 power is equal to 1 preceded by a minus sign. So that's now minus 1. So minus 9 to the 0 power equals minus 1. Now how about minus 9 enclosed in a parenthesis raised to the 0 power? So the everything inside the parenthesis is the base. Since this base is non-zero raised to the 0 power, and that's simply equal to 1. So a to the 0 equals 1 serves as the unifying link of the entire exponent system. Without it, the continuity between positive 0 and negative exponents would fall apart. It made all 7 laws of exponents consistent, complete, and unbreakable. Because of its importance, mathematicians and educators recognized it as the 6th law of exponents, and not merely a special case of the quotient of powers rule. So we can say this simple yet powerful rule transformed mathematics beyond what we could ever have imagined.